six PPT also. Just be sure that we went over everything. So we went over share strength and circling modulus. Yeah. So seventh week is dedicated to your share strength again. So we talked about the shear strength parameters, which is C and phi. Just a moment, please. Hello. Good afternoon. Okay, okay, okay. I got to know where I have. Okay. Yeah, yeah. I have. I am in the session. So that was from the NPTEL team. Okay. So we were talking about C and phi. Yeah. So where is this? Okay. C and phi. So think about it. Basically, these are not fundamental parameters, which we will discuss further. Uh, in the sense, why they are not fundamental parameters is because they, when I tell you that this is the C value and this is the phi value of a soil, it is not that you can say much about the soil from C5 value only. You also have to tell me that how you got this value. You also have to tell me in what state your soil was. Was it saturated? Was it dry? Uh, did you allow the drainage? Did you not allow the drainage? So these are subject to the shear parameters we are right now talking about. This is frustrating. They are these are subject to certain conditions. We will be talking about these conditions further when we discuss what kind of tests do we do to obtain these parameters. Please give me a moment to bring in the PPT. Okay. So there are some tests that we are doing. There is this uh, direct shear test, and then there is this triaxial test. There is this unconfined compression test and vein shear test. Among these, this is the most important test for the soil that can tell you, mm, we can't say the exact true behavior, but it is more accurate than all of these because there are some constraints that we put to the soil in these kinds of tests. So for direct shear test, what we do is, first let's talk about the behavior of soil in, as I mentioned in the last lecture, when we compress the soil, it has good compressive strength. It does not fail in compression. But what happens is that if you compress the soil, there is already a confinement pressure here, and if this stress gets too high, such that a reactant of the stress kind of starts working on this soil, you get a shear failure, isn't it? So you will have a shear stress on these faces, something like this. Uh, so shear failure you will get in the soil, something like this. This will be the failure. Obviously, this is not what happens into a confined specimen. I'm talking about, let's say I take a cylindrical soil mold and I compress it. So you will see some bulging here, and then you will see a failure in this direction. You must have already studied these strength of materials course in which you study about the normal stresses and the shear stresses, and you know that the shear cracks are always in this diagonal uh, direction. So this is what we call the failure plane. This failure plane is oriented based on what kind of loading you are providing with the soil with. So the kind of loading I am providing will determine what will be the angle of this failure plane. But when we talk about direct shear test, we don't let the soil decide its own failure plane. What we do is we have a box that is uh, built with an upper and a lower half. We fix this like this, and then we fill it with soil. So because it has an upper and a lower half, we push this upper half in this direction and cause the soil to shear on this interface. So this becomes the failure plane. But this is not the natural failure plane that the soil would have decided on its own. This is a forced failure plane. So the direct shear test will give you the C5 values of the soil, but one of the limitations is that they are not the internal intrinsic values. And the other limitation of direct shear, I am assuming that you have already studied this in class. That is why I'm only discussing the limitations and not the test itself. We can go on with the test here. If you see, we provide shear force here. What basically we have is this kind of a box which is clamped, and then we have a loading hanger, something like this, and we apply some weights here, and this kind of produces some displacement in this direction. And we monitor the displacement and the stress applied through this load, and we calculate the load versus displacement curve, and we do this for three readings, and we calculate the shear envelope, and from the shear envelope, you do this for three readings, you will know the normal stress already you are providing over here, maybe at 10 kPa, 20 kPa, 30 kPa. You do this for three loadings. This is the normal stress. So you do this for 10, 20, and 30. And you will see a peak when the loading is increasing, and then it suddenly reverses back. You know that point is your failure. Excuse me. You know that point is your failure point, and you plot it here. Failure, 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 and you join. So the intercept will give you your C value, and the slope will give you your phi value. So that is how you perform the direct shear test. I will not go much into the details of the tests, but for one thing you should know is that the failure plane is host. The second thing you should know is that we usually perform this for sands because it does not have the ability to tell us about the changes in the pore water pressure. So basically, what you will study in consolidation is that in a soil or any kind of matrix, there is this, you can say, analogy in which we say, let's assume that this is a glass container, and this has these discs made up of cork at three levels. These are resting on springs. So you know that this material is not impervious, it just has low permeability. It's not that, uh, assuming that these are waterproof interfaces, if you try to push this down, these springs, the water will come out of the top layer. But if there is only the spring, there will be no resistance to the movement of the spring. But because you know this material has a lower permeability, the flow of water through this material is low, what will happen is that when you have applied all your load, the amount of displacement that you should see, it is not there, isn't it? So there is a lot of stress that you are providing uh, uh, at an instant. If there was a lot of displacement, so we could have said that all the load has been absorbed, but it takes some time for this load to get absorbed. So un- these springs will start slowly compressing, they will not instantaneously compress, and until then, until these springs take the whole load of the external load, whole of the external load, the load is carried by the water. So here, what happens, if you had a piezometer here, it would have been at this level. And at the instant of the loading, this would have risen up because all the load the water is carrying. This would increase, and then slowly, based on the permeability of these materials, the water would come out and the load would get transferred to the springs, and this level would decrease, and this is what excess pore water pressure is called. It is in excess to the actual, it is not the actual pore water pressure. Actual pore water pressure is hydrostatic, it is same in all directions. This is excess pore water pressure due to loading and low permeability. So if you load a low permeability sample in direct shear test, what will happen is that when you're loading, all the load is getting carried by the water, and you don't have the mechanism in the direct shear test to calculate the excess pore water pressure. So you can't actually do justice with an with an undrained loading test in which you are not allowing the drainage to take place. And undrained loading test does not mean that I am restricting the drainage here by some physical boundary. It also means that the permeability of the material is so low that the rate of loading that I have applied actually uh, means that the water did not get the time to dissipate. It did not get the time to flow out in that time period, and thus it is an undrained loading. Not because it is not open to drainage, but because the conditions are such that the drainage did not get time to take place. Is it clear to everybody? Is it clear to everybody?
Yes, madam.
Mm, I think I, if you get confused somewhere based on what I am saying or what I mean, please just raise a hand and let me know mid sentence, because I don't want to go off in a tangent and then realize that people did not follow. Okay,
Okay. Okay.
thank you. So we discussed that there are two kinds of tests. First, there is drained test, and there is undrained test. So what is a drained test? In which drainage is allowed both physically and temporally, meaning that it does not mean that you are, if you are not confining, if I have a clay sample and I don't confine the outer boundaries, so the water is free to flow out, and then I load it, it does not mean this is a drained loadage. Drained loading. Drained loading will be when the rate of the loading is slow, such that the water that is generated, the excess pore water pressure that is generated due to the loading gets time to dissipate. Okay, so drained tests, that is why usually drain tests are performed for coarse grained soils, because they are freely draining, they have high permeability, they don't get excess pore water pressure buildup. And undrained tests are performed for uh, fine grained soils. Fine grained soils can also have drained tests, but they are very, very slow, very slow. Uh, so the yes, please.
Madam, in a drained test, as you mentioned, it is for
Yeah.
a coarse grained soil.
Uh,
Since the permeability is very high,
Yes.
why we conduct a very longer period of testing time?
No, we don't conduct a longer period of testing time. I said that undrained, fine grained soils, for fine grained soils, we usually perform undrained tests, but we can perform drain tests on fine grained soils, but they are very long because the drainage, the rate of loading has to be so slow because the permeability is very low.
Uh, Madam, I could not understand here. CD test is normally done for which materials, madam? CGS or FGS soils?
Consolidated drained is done usually for CGS
In
because for
CGS soil, okay. In
yeah
CGS soil, permeability is very high.
uh, yes
Yes, no, madam.
yeah
Permeability is very high. Madam,
consolidated
can you hear,
drained.
madam?
Yes, permeability is high.
Hello,
Yes, can you hear me? Hello, can you hear me?
hello.
Can you hear me? Hello.
Yes, madam.
Okay, sorry, this got disconnected. Can
Yeah,
you see
some
my
error.
screen?
Yeah, I can see it, madam.
I'm still sharing now.
Yeah, yeah.
Okay, huh. So yes, you were saying.
CD test is generally done on coarse grain soil, which are
Hmm.
highly pervious.
Hmm.
Highly pervious means it takes generally less time.
Yeah.
Then why CD test? Usually they mention in a number of sources that it is a slow test.
Slow test only for fine grained soils.
So CD also they are mentioning as a very slow, madam. Fine grain soils is a quick test. UU test is a quick.
Yeah, UU test is quick because basically it is a comparative way, na? See, uh, um, let's talk about triaxial testing. I will address your question in this, okay? But
Okay,
let
madam.
me give a little bit background about triaxial testing.
Okay.
So in triaxial tests, you must have studied that we have a sample which is cylindrical. It is important that the sample is cylindrical because in a 3D coordinate, we are taking an axisymmetric case in which your sigma 3 equals sigma 2. So if the stresses in this direction will be sigma 1, sigma 2, and sigma 3, when you take a sphere, all the stresses will be same. When you take a cylinder, then the stresses that are along this axis will be different and the rest of the stresses will be same. This makes our problem easier because now we have to deal with two principal stresses instead of three. There are instruments for polyaxial testing, especially for rocks, in which you have three we don't have this kind of you don't need a cylindrical sample, so it has um, the ability that you can take different sigma 1, sigma 2, and sigma 3, and that is what is called true triaxial testing, and that will give you the true behavior. But it is quite complicated, expensive, time taking. So basically, um, this serves us well enough for us not to indulge in, um, except for indulge in triaxial test, multi-axial testing, except for in research. Okay, so in triaxial testing, we have, this is our sample. Okay, so we have two stages. The first stage is you have a sample. The first stage is about preparing your sample, as in, for example, in the field, there is some density of the soil. Uh, I get this soil from the field. Let us say that it had a confining pressure of, let me say, sigma 1. Okay. Now I want to test this soil in, I want to get the strength of the soil, but when I remake a sample, because when I have taken this out, this stress was released, isn't it? So I want to get my sample back to this condition, which I am actually testing, isn't it? When I take the sample out, this sigma 1 got released, and the sample now is different than what actually is present in the field. So I will take this soil, and it also depends on what kind of test I want to do. Um, I want, for example, the confinement was 100 kPa. What I want to do now is I want to take this soil and confine it with the confining pressure of 100 kPa, let's say, so that I replicate what is present in the field. And if I want uh, to know how the soil would behave, it was unloaded. If it was unloaded, I'll only go up to 50 kPa. Then this soil will be over consolidated. I hope you have studied about normal consolidation, normally consolidated and over consolidated soils. So if not, please let me know. Uh, so the first stage is preparing the sample. So what we do is we take an outer cylinder and we fill it with water, and we fill it at some pressure. We fill so much water such that uh, the specific pressure that we want uh, to test the soil at is reached. This is called the first stage, which is the consolidation stage. So what we are doing is we are isotropically consolidating the specimen. This is called isotropic consolidation. Why it is called isotropic is because water has a hydrostatic force in all directions which is equal. This is not same as um, uh, confining your soil in a container like you do in consolidation test. In consolidation test, you have a ring-like apparatus and you fill your soil inside this. Okay, and then you apply weight here. This confinement here is very different than the confinement in triaxial test, because in triaxial test your lateral boundaries are free to deform, while in consolidation test your lateral boundaries are not free to deform. So in consolidation is in odometer test that you study in consolidation. It is not isotropic consolidation per se. Isotropic consolidation is this one, the first stage of the triaxial loading. So once this consolidation takes place, so for the consolidate, the stage is for the sample preparation. It can be of two types. It can be consolidated or it can be uh, unconsolidated. Consolidated is when you let the water from the sample escape, you let the sample deform under this consolidation load so that it reaches an equilibrium. This is so that you reach a particular state that you are wanting to get the shear strength. Unconsolidated is you load and you don't wait for the drainage to happen. So, Arav, your question is why CD test is long? Because uh, in sands, even uh, when we say fast drainage, at least you will wait for 1 day for consolidation to take place. At least you will wait for 1 day for to say, but clays may take even up to 3 months for complete consolidation to take place. That is why unconsolidated test is just you gave the load, you applied the load, and that's it. You can move to the next stage. Consolidated test is when you have to wait for the sample to um, achieve equilibrium under this particular loading. You got me?
The problem for me here is
Yes.
the coarse grain soil actually consolidation topic is not there. This is completely instantly the entire water will go out. No, why we have to wait for water to go?
See,
That
the
is my question.
coarse grain soils usually, when you're talking about coarse grain soils, we are not talking about gravel here. We are talking
Okay,
about sands and silts because you see, gravel size is not conducive of triaxial testing. For
okay,
basically, to be more fair, whatever we want to know about sands or gravels, we get it from the direct shear testing. We seldom do triaxial testing for sands. We may do if we want to study some dynamic behavior or liquefaction behavior. But otherwise, if you only want the C5 behavior, you can get it from direct shear test, which is which is relatively quite easy. So mostly this is used for either silts or clays. Um, you get me?
relatively pervious material than the finer grain.
No,
Yes. Uh,
triaxial test is usually done for relatively less permeous material because
yes, madam. CD test I am asking. CD test is
okay,
relatively pervious soils compared with the clay.
no,
Is it?
no. That is not it. It is a type of test. You can perform it with any test, any soil that you want, but it is a
Okay.
preference. It is a preference. I would not want to do consolidated drain test on clay because consolidation itself will take me about 6 months, and then the loading another, I don't know how much time. Because
Okay.
uh, and in fact clays, you should know that this test is performed at saturated state. So uh, in triaxial testing apparatus there are some probes that can tell you if the material has is saturated or not. And I know one of my colleagues that were performing consolidated consolidation tests, not triaxial tests. They were creating a consolidation tank for um, black cotton soil, and it took them 5 months to just saturate the sample, only saturate. Then they had to consolidate, and then they had to load it. So it is a matter of preference. If you have the time, the resources, you go with CD test. If you want a quicker solution, you go with CU test. Or CU test is like it is a middle ground between UU and CD test. This is preferred. Okay.
Yes, madam.
Now it just comes to the practicality. You understand what I'm saying? Theory kept aside, uh, practically what you would do if it took you so much time. It's not always. If you have a C5 soil, if you have a sandy clayey soil, sandy silty soil, obviously it will not take that long, but there are some cases in which CD test can be quite long. Okay, so we talked about we talked about the first stage, that is the consolidation. It can be consolidated, it can be unconsolidated. Second stage, usually when we have fine grain soils, usually we go with consolidated. We don't go with unconsolidated, because when you start loading, then the consolidation will obviously take place. Uh, so UU test, in UU test, sorry, did I say CD?
Yes, madam. Till now we discussed the CD only
No, no,
about course grade.
CD,
Hmm.
CU, UU, CD.
You have not discussed it just now.
Okay, 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 okay. So we talked about the first stage, that is the consolidation stage, and the second stage is your loading stage. So during consolidation stage, you have loaded your sample isotropically to a particular stress. Now, what you do is you don't apply shear stress. Actually, like in direct shear test, what we did was we applied a tangential kind of stress relative to the other portion of the body. What we do is we increase the stress. This is called the deviatoric stress. Sigma 1 will be on this face, and we increase and increase and increase this until we see a shear failure because of the imbalance between the two principal stresses. Okay, so we are inducing a shear failure, not providing a shear loading. We are providing normal axial loading but inducing a shear failure. So here, if you see that the soil will fail at the weakest plane by default, it does not predefine the angle of failure. And the second stage can be either drained or undrained. So if it is drained, it is fast. If it is undrained, it is slow. So drained and undrained only means that if you are opening the valve for drainage or not. So another thing that drained and undrained tests signify are when you don't allow the water to move out, given that your sample is saturated and you assume water to be incompressible. You are assuming water to be incompressible, soil grains to be incompressible. What will happen is that there will be no volume change. You will not see any change in the height of the sample. You will only see changes in the effective stress through excess pore water pressure. But in drained, you allow this water to get out, and the excess pore water pressure that was dissipated during the loading, it also gets dissipated. So you will not see generation of excess pore water pressure, but you will see uh, change in volume of the uh, sample. Did you understand this?
Yes, madam.
Okay. So undrained shear box test was carried out. So this is the triaxial testing apparatus. If you look at it, this is the inner sample and we confine it within out excuse me outer cylinder, fill it with water at a pressure which is called the cell pressure. Cell pressure forms the third me, principal stress, sigma 3, and then we this is the loading from the top. We give an axial strain to this whole setup. This is the apparatus where we can measure the changes in the excess pore water pressure. So, unlike a direct shear test, this can be done for both drained and undrained cases. In drained cases, what you will see is displacement. You will not see excess pore water pressure. In undrained case, you will not see displacement, but you will see excess pore water pressure. That is the main idea behind the triaxial test. So this is the sigma 3, sigma 1. Okay. So strain and deviatoric stress. You calculate, you get this kind of a curve, and then you get a failure somewhere at the peak. At these failure, if you plot these failure loci here, you will get an envelope from which you can get your shear strength parameters. Total stress, okay. So earlier I mentioned that C and phi are not uh, characteristic parameters. Um, Excuse me, just a moment, please. हेलो। हाँ। अस्सलाम वालेकुम। कैस कैसा रहा मुझे? हो गया? आप डर गए? आप डर गए? सच्ची? नहीं। एक सेकेंड। मेरी मेरी क्लास है अभी। मैं क्ला मेरी क्लास है अभी। मैं आपको कॉल करती हूँ। अरे प्लीज, अबूजी प्लीज। ओके बाय। अबूजी बाय। ओके। So we were discussing that these are not, we can say, characteristic parameters, as in that when you perform a CU test, when you perform a UU test, when you perform a CD test, you get different values for the same soil because these parameters depend on the state of the soil. So they are not fundamental, actually, should say fundamental. Okay. Fundamental is something that will not change if the state of the thing changes. For example, uh, let us say you have a hydrogen ion. No matter what this ion is bonded with, in what form it is, in physical, in anywhere in the world, when you say a hydrogen ion, you know it will have plus one charge. That is a characteristic, fundamental property. You will know that it will have one unit mass. So these are fundamental properties that do not change with the physical state of the material. But C and phi are not such properties. They are not fundamental in this sense. They are easy to determine. They are very informative given that we know where we got them from, and they are convenient, but they are not fundamental. Okay. So as you see here, so when we write the shear strength formula, Mohr Coulomb formula, which says tau is equivalent to Cu plus C. When we use the Mohr Coulomb formula, it is important to know that we are talking about the effective shear stress parameter. We're not talking about the total shear stress parameters, because uh, total stress is dependent on the water content of the soil. If it is saturated, the total stress will be high. If it is unsaturated, it will be low. But effective stress is constant. It does not depend on the water content, isn't it? Because total stress minus the water pore water pressure will give you effective stress. So effective stress is more fundamental than total stress in that sense, but it still depends on the density, the denseness, the OC, over consolidation condition. It does depend on that, but at least it does not depend on the immediate water content of the soil. So we are basically talking about a more fundamental, relatively more fundamental properties which are the effective stress properties. Okay, we are not all, but when you are doing your UU test, see in CU test you have uh, consolidated the specimen. That means that you have allowed the drainage. Okay, so you get your effective parameters uh, from the CD test will give you effective parameters. This will give you something of a mixture. UU test will give you total parameters because you are not letting the water drain out. Some of the load is getting carried by the water, and the parameters that you get are of total stress. So this is undrained loading. This is the effective stress envelope with no cohesion. When you see a prime here, you should know that this is effective stress. These are the total stresses. If you see, basically what happened was you saw an effective stress envelope like this, but the total stress envelope was something like this. This does not mean that at different stresses, strength of the soil is different. It just means that the locus of the Mohr circle will be different, leading to a flatter or a steeper slope. So you see, same tests will have same Mohr circle. Only difference is that you will have a different uh, locus for the center of the Mohr circle. The radius of the Mohr circle will be same. So this is the undrained total stresses. These are the drained effective stresses. Okay, behavior of soil under shear. Before going to this topic, familiarity with the following terms are needed. Overburden, effective overburden pressure, normally consolidated clays, over consolidated clays, pre-consolidation pressure. Okay, so yes, please.
Madam, small doubt, madam.
Yes, please.
I don't know about from any source I'm asking this question.
Okay.
What is the extreme higher values of C and phi value for which soils you can find this highest value of phi or highest value of C as per you know,
So,
whatever you have source, madam.
okay. So, as I said, that exactly I will discuss it here only. When I say that C and phi are not fundamental values, it means that they are different for same soil in different conditions. I will tell you, for example, what will happen here. Let me take a sand, same sand. I'll take two samples from it. I have prepared this sample at a relative density of 60%. And then there is another sample that I have prepared of the same soil at a relative density of 95%. So I will see a phi value of maybe up to 38 degree even. But here I will see a phi value of 24, 26 degree. Mind it, this is the same soil. You understand? But if we talk about different kinds of soils, gravels have higher um, phi values. They have more than 42, even 45 degree because they have greater interlocking. And then within the gravels also, it will depend on the shape, angularity, or the denseness of the material. Okay, same is the case with clays. We say that clays have high cohesion, isn't it? But this also depends upon if it is normally consolidated or over consolidated. So, what does normally consolidated and over consolidated mean? Keeping aside the explanation or the definitions that are given, keeping aside the definitions given in books, let's simply talk about it. For example, let me say that, okay, for this is just an example. Let us say that I have folded some clothes and stacked them. Imagine that these are some jackets. Okay, so you see, when I stack them like this, they might be quite compressible, isn't it? I'm just stacking them. If I sit on it, it might compress something like this, isn't it? Now I have a suitcase in which I have stuffed these jackets and I've compressed them to a bit. Okay, now you see this state, something with the pen. Okay, this state and this state of the same pile are different. But when I say OC and NC, this also is relative. For example, some child comes and he steps on this pile. Obviously, uh, this let's say that these are denim jackets. So I put a child on it. They may or may not compress based on the weight of the child, isn't it? But if I put an adult over it, they will definitely compress. Okay. So when I'm putting a load on a soil, whether it is NC or OC does not depend on the soil itself, it depends on the load. That is why we say that the strength of the soil depends on the loading. So if the soil uh, was initially, let us say it had a um, confining pressure of 100 kPa. Now I come here and I put some weight here, 50 kPa. We say that the soil is over consolidated because it already knows how to act when 50 kPa was applied to it. So it will not compress. You have to apply more stress than it already has seen for it to compress more. So this is this is OC. Something wrong with the pen. So this is OC state. The soil is over consolidated. It's already too consolidated. Now if I come and put a 500 kPa load, now this will be normally consolidated because now the soil will start compressing as if it was for the first time. That is what OC and NC means. It is not a type of soil, it is a type of loading condition. So, this is something that people get confused with all the time. So, we say that clays have high cohesion, but you should know that NC soils have zero cohesion. We take cohesion for NC clays to be zero. Cohesion for OC clays is higher. Okay, so if you here see that now your values of the shape parameters not only depend on the condition of the soil, it also depends on the condition of the load you are putting on the soil. So the first thing we talked about was drainage, how your C5 depends on drainage. Second thing we talk about is the density of soil, the state of soil. Third thing we talk about is stress history, okay, or the loading history. So these are the things on which your soil behavior will depend, and your C5 values will change based on this behavior. Okay. So your question was which have high phi and maximum C. So maximum phi we can say gravel with very high relative density. Okay. And then we have clays, highly over consolidated clays. Okay. We can have high C for this. Is does that answer your question?
Yeah, madam. I got the phi value you have mentioned. Approximately it reached to 48 degrees,
Yeah.
45 or something.
Yeah.
But I couldn't get the answer in the numerical form, but theoretically you have given explanation, good explanation.
Yeah.
Numerical, I'm asking how much kilopascals maximum, something like.
I
Some other time you can answer, madam. No problem. From any
yeah.
source.
I think even up to 50 kPa we can have C,
Okay,
but
madam. Okay, okay, fine.
50 kPa there can be, it can be higher, but I can't remember right now,
Yeah,
like if I have seen it or not.
yeah, yeah. It's okay, madam. Thank you.
Okay, so
And madam, one more can I ask you?
yes,
Small.
please. Yes, please.
It's a fundamental question. Since I am not clear with I am asking.
Yes,
As you
please.
mentioned, the shear is going to take place because of the compressive load in second stage.
Yes.
Yeah, is it shear will also takes place due to tension or no, madam? That's what I want to ask. Tensile load
No,
also will make a shear or only compressive loads?
no. See, tensile loads also make shear,
That,
but we are we don't talk about tensile. We don't talk
yeah,
about tensile loads in soils because soils don't have tensile strength. But same thing happens in concrete when you have concrete short columns, when you have even concrete cube tests you used to do, when you let us say
even in metals also you have a tension.
metals are different because metals are they have a malleability. They're not brittle, isn't it?
Yes, madam. Yes.
If you extend a metal, you will see necking,
Hmm.
isn't it?
Yes, madam.
Um, in you're talking about tension as an extension test, or you're talking about tensile forces. Do tensile forces cause shear?
Yeah, madam. The tensile forces which causes the shear
Okay,
failure in
see, if I have an irreg something happened to the pen. Okay. Battery.
Yeah, this question I am asking because of
Just,
pile foundation, we
yeah,
get a
yeah.
tension. Transmission towers also we get a
Just
tension.
a moment, just a moment. My battery of the pen that I
Okay,
use for teaching just died. Let me just connect it to the charger and I'll
yes,
get
ma'am.
back to you. Okay. Uh, See, I said that there was compression here and then there was lesser compression here, because of which there is a resultant shear force. This can as well happen if you had an extension in all directions, isn't it? You will have a shear but in opposite direction. You understand?
Okay, ma'am.
So it is an induced shear. This is not pure shear. This is
Yes.
shear stress that is induced due to unbalanced forces on these elements, and they can take place in this can take place in compression as well as in tension. Just the sign will be opposite. If you have a shear in this direction here, you will have a shear in this direction, that is like this. Here you will have something like this. Okay.
Right, madam.
Okay, so the behavior of soil under, so we talked about these normally consolidated, over consolidated. Pre-consolidation pressure basically means that uh, the pre-consolidation pressure is the pressure at which the soil was in its original state. Like if I take a sample from here, um, and then I, whatever stress was on this sample, uh, or not right now, but maybe in its history, it had, basically when we're talking about what kind of stress it has, it's mainly about overburden. If I take a soil here and it is like 8 meter below the ground, so it will have, if the gamma here is 18, let us say 10 meter, so this will be 180 kPa. And then let us say that it has a k value of uh, 1 minus sine phi. At it has a phi of 30 degree, it will be 1 by 2. So it will be 90 in this direction, this will be 180 in this direction. So this was the original pressure on the soil. So given that this was the state you find the soil in, and this has been, soil has been depositing only, you will know the pre-consolidation pressure. But now if somehow, some due to some action, like you got an excavation, or you due to erosion or something, what happened was, one some of the overburden over this soil was removed. Now instead of 10 meter, you only have 5 meter. But earlier it was this. Now you have a lower pressure. So the pre-consolidation pressure will be the maximum pressure that the soil has experienced in its history, because it will remember this pressure. Why? it will remember is because soil is not an elastic material. It's not like a spring that you compressed it with 180 kPa and it got compressed, and then you took, let's say, 100 kPa back, and then it sprung back. It will not, it will remember. It will have plastic loading. It will have changed its shape to accommodate this 180 kPa, and now it will uh, it will change its nature based on this. Okay, so the pre-consolidation pressure will be this even if you remove the loading. But let us say that I build a building here and add 100 kPa more. This soil will the loading will increase to 280 kPa, for example, and then the new consolidation pressure is 280 kPa. Basically, the pre-consolidation pressure is the pressure on the element of soil, maximum pressure on that element of soil that might have fixed the structure of this soil in a particular way. Okay, so shear strength behavior. We're talking about dry sand, there will be no pore water pressure. Saturated sand, the pore water pressure will be zero due to quick drainage. Then we talk about dry, dense sand. Do we talk about dilation, negative pore water pressure, critical density? I have not mentioned this. I thought that it was advanced. Okay, so let me mention it briefly. As I was saying, that C and phi are not fundamental parameters of a particular. So why use them? Because of convenience. Because this was the classical mechanics on which the soil mechanics was built. But since then we have defined other parameters that are more fundamental than C and phi. For example, we talked about critical state of soil. Critical state of soil means basically, so same sand I will have in a loose form and a dense form. Okay, when I load this dense form in shear force, this, and when I load this loose form, this is void ratio. I see that the loose sand will try to compress something like this, and the dense sand tries to loosen, and both of these try to reach a state of constant volume, as in beyond this, if I load this soil, there will be no volume change. This is the critical state of soil. Here the uh, q by p ratio will be your, so the void ratio here will be one of the parameters that are that is fundamental, as in it does not change. It does not matter if your soil is loose, it does not matter if it is dense, it does not matter what is the density of the soil or whether you are draining it or not. It just means that when you load it from any density, it will start to reach and try to reach a critical void ratio. Okay, so same kind of thing happens with fine grained soils where you have a normally consolidated and an over consolidated soil. You try to share these and you will see that they will try to reach a critical void ratio. Okay, so this is called dilation of sands because you see here the volume is increasing, here the volume is decreasing. This is the dilation. Okay, this is what we are talking about here somewhere in here. Density at which there is no increase or decrease in shear strength when the sand is maintained at constant. Okay, uh, mentioned dense sands dilate during shear and the shear strength of the sand increases because of the development of negative pore water pressure if movement of the pore water pressure is restricted. So when you're talking about the pore water pressure, you're talking about mostly fine grained soils. I don't know why it's written like this, but this is the concept of the critical density. And next we have, so volume decrease, normally consolidated, you will see a slight decrease and then increase in over consolidated. And you will see a peak kind of behavior for over consolidated, but this kind of behavior consolidated. And you see kind of same thing for sands, but dense sand is analogous to over consolidated clay and loose sand to NC clay. So you see that they both try to reach a critical void ratio and they try to reach a constant residual stress at at this stage when they reach this critical void ratio. You see, whatever you increase this, whenever you increase the strain, you will not see any more increase or decrease in stress. That's the critical state. Then we have the vein shear test. Vein shear test, what should I say about these are for, this is for clays. We basically take this kind of a equipment and we rotate it in the soil, and through the vein shear test we calculate the torque that was required to make the rotation, and based on that we calculate. This is quite straightforward. Okay, so I think we can discuss some questions now because otherwise it will be very late. Okay, direct shear tests were performed on a dry sandy soil. Size of the specimen was 2 inch by 2 inch by 0.75 inch. Test results are given below. Find the shear stress parameters. Okay, let's try that. So we have a normal force, we have a shear force at failure, and test results are given below. Find the shear stress parameters. ठीक है? So this we just need to plot a graph for this. Let's do that. Normal force is 20, 30, 70, 100. Array. Then we have shear force. Let me get it from here. Okay. So one of the things that we did not discuss, which was mentioned here, is the area ratio. Basically, what it means is in your direct shear test, what happens is that as you are displacing, obviously this much displacement does not happen, but let me say that, let me exaggerate it a bit. It's only a few displacement, but let's exaggerate and say that I have a displacement of this much taking place between the upper and the lower boxes. So initially, when I had the boxes aligned like this, the whole area was uh, taking part in generating the shear resistance. But if you see here, as the box moves, the area of contact between the upper and the lower soil parts, lower box, is getting reduced. So we have to take that into account when we are uh, performing the direct shear test. So we have to uh, make an area correction. Just saw it somewhere.
Only in triaxial and UCS area correction is applied, madam. Sir, direct shear, we did not apply area correction.
It's a different kind of area correction. It's not the area correction for direct shear and triaxial is different. The area correction that we apply there. This is a bit different. Uh, one, okay, let me check, huh? Just give me a moment.
And the deformations are not given, madam, in this example.
No,
Then how you calculate, madam? Only loads are given.
yeah, just a moment, please. Uh, okay, I might have. Uh, I will cross check this, but I will. I definitely studied this in the geotechnical in one of the geotechnical manuals when I was doing this test. But I can't seem to find it right now. I think it was in the. Just a moment. Uh, just a moment. It's taking some time to load. Okay, I will look into it and uh, I will let you know. I'm not able to find it. Okay. Nonetheless, let's proceed. So the side is 2 inches. The area is 4 inches. Um, let's convert this to feet. Divide by area. So we will have no normal divided by area. Square. Okay. Then we will have the shear stress, which will be this over this. Yeah. This we have C value 5.2, and we have a tan phi of, or we can say uh, this will be the phi value, which will be tan inverse of 0, 0.596. I want this in degrees. So it is about 30.9 or 31 degrees. So these will be our C5 values. So basically, for normal shear test, for direct shear test, what we do is at different normal stresses 20, 30, 70, 100. Normal stress is something that we apply on the top of the box. So first we'll apply 20 pound per feet square, and then we will start shearing and we calculate the shear force. And then we do this again 3 4 times so that we get three more values which we can convert to a straight line then. Okay, so the next question is, following are the results of 4 drained shear test on an over consolidated clay. Drained direct shear tests on OC clay. Diameter direct shear test. Okay. Diameter of specimen is 50 mm. Height is 25 mm. Determine the relationships for peak shear strength and residual shear strength. Okay. So what we do here is, let me question two. Okay. Normal force, shear force. We have been given the area. We have been given the diameter. Diameter is 0.05 meter. So right. Then we have the height, which is 0.0. Then have the area, should be okay. So what we can do is let's calculate tau at failure and residual tau. Okay, this will be normal force over area, but we want this in kilonewton. Okay, so we will have this will be for shear force, this will be for this thing. Okay, so these are the values. We can just develop. Series 1 will be at failure, x will be this, y will be at failure. Then the next series will be residual, x will be again this, y will be this. So what we can do, we can add a linear here. And we can do is we can put a linear trend line here. So you see, I should add the legend. So this is the failure envelope, and if you see, this is higher than your residual envelope. So if you remember, I mentioned that there is like this residual strength is more fundamental than your failure strength, because your failure strength will depend on the type of test, but your residual strength will always be something that is inherent to the soil. And let's add the equations. So for we have C and phi. For residual failure, C for residual will be about 0. For this, it's 38. Phi is 0.641, about 15 degrees. Here it is 57 degrees. Oh, so these are the C5 values that you obtain. This is the residual strength. You will have a lower phi, lower C, but this is more fundamental to the soil as compared to what you will see at failure.
Madam, these are without area correction. No?
Yeah, because they are direct shear tests.
These are direct shear, madam.
Yeah,
Uh, okay, direct shear and cylindrical sample.
yeah,
Okay, okay.
okay. So this is a triaxial test. A consolidated drain test was conducted on a normally consolidated clay. The results are as follows: sigma A and delta sigma D at failure. Determine the angle of friction, angle at failure plane that the failure planes makes with the major principal plane. Find the normal stress and the shear stress on the failure plane. Determine the effective normal stress on the plane of maximum shear stress. Okay, okay. This is same. This is same. This. We did this, no? Okay. So just a minute. Consolidated drained triaxial test conducted on.
Madam,
No, yeah.
sorry, madam. Can you zoom it, madam? It is not visible, bro. Yeah, madam. Yeah. Yes, madam. Thank you.
Okay. So as I mentioned earlier, for NC soils, C is almost safe. Why? Can somebody tell me why? Okay. So what is cohesion? Cohesion is the ability of the material to stick to itself. It is the affinity of the materials, of the particles of a material within itself. When we say that the soil is normally consolidated on a E log sigma graph, when your soil is over consolidated, it shows a lower tendency for change in volume with increasing change in normal stress. But as it reaches its reconsolidation pressure, now that the soil history, this the maximum load that the soil remembers, or to be more precise, the maximum load under which plastic deformations had happened that had made the soil to restructure itself, it is reached. Now, beyond this, this is new territory for the soil. If you load the soil beyond it, you will see that it shows a higher tendency for volume change. It suddenly becomes less stiff. Okay, so the resistance to the volume change, if you see here, is because uh, now the soil grains are facing something that they don't know about. So, this reduction in stiffness, high, uh, and basically reduction in strength also, basically means that the affinity that we talked about between the particles has been overcome now. So for NC soils, we take C0 because now the um, uh, mechanism for sh- shear resistance cannot depend on C. It is there only until your soil is over consolidated. Once you overcome this pre-consolidation pressure, you will take CE0. Okay. So for NC soils, tau F equals sigma dash tan phi dash C dash is 0. And the major principal stress will be sigma 3 plus deviatoric stress. Sigma D basically in your triaxial loading, you have sigma 3 everywhere, and then you apply an extra deviatoric loading, and this is your sigma 1. So your major principal stress is 140 plus 100, which is 240, and your minor principal stress is 140. You know, for C0 soil, we have from the Mohr Coulomb diagram, this is sigma 1, this is sigma 3. So this is the radius, which is sigma 1 plus sigma 3 by 2. This is sigma 1 minus sigma 3 by 2. So sine phi is Sigma 1 minus sigma 3 by 2, sigma 1 plus sigma 3 sine phi 44 minus 140 plus 140. Let's calculate this. This comes out to be about 15.7 degree. So we calculated this. Now we need to know the angle that the failure plane makes with the major principal plane. Okay, so this was about 15 degrees. Now in your triaxial test, we have something like this. So in the Mohr circle, we know this angle is 2 theta. So just give me one minute. Put this down. So this angle is 2 theta, and if we take this, this will be 90 plus this angle equals theta. Yeah. So this will be 90. The triangle, you know, if a triangle has an external angle, it is the sum of two opposite internal angles. The angle here will be 45. Okay, let's take this complete. This is 90. So 2 theta equals 90 plus 5. So theta equals 45 plus pi by 2, which will be 45 plus 7.5, which will be 52.5 degree. So we have taken this angle, this triangle here, and equated the external angle of 2 theta to the sum of phi and 90. So this came to be 52.5. Find the normal stress sigma and shear stress tau f on the failure plane. So sigma on the failure plane. Either we can do this from here only. Uh, this is 2 theta, and this will be sigma 1, this will be sigma 3. You can either do it geometrically or you can calculate from your this, which is given as sigma 1 plus sigma 3 by 2, sigma 1 minus sigma 3 by 2, cos of 2 theta, and tau f is given as sigma 1 minus sigma 3 by 2, sine of 2 theta. Basically, it's coming from here only. We are trying to calculate this and this. So this is 90. This will be 180 minus theta. Basically, this will be 90 minus theta. And 80 equals 90 plus 90 minus 2 theta plus this. This calculation. Calculating this, we will get 178.54 kilonewton per meter square. Calculating this will give us 50.23 kilonewton per meter square. Determine the effective normal stress on the plane of maximum shear stress. So basically, maximum shear stress will be this, na? Okay. So this is the maximum shear stress. So if I draw it here with the center, it will be 90. So theta will be 90, theta will be 55, and you have a 45, a crack at 45 degrees to the horizontal, which will be a maximum shear stress. And what we need is to find the effective normal stress. Here will simply be cos 90 will be 0, sigma 1 plus sigma 3 by 2, which will be plus sigma sigma 1 क्या था? This will be 72. 70?
Sigma 1 is 244, madam.
244.
Yeah,
Okay. So how much does this? Uh,
192 you get.
okay, 190.
Yeah.
Okay, so this is sigma n on this. I think that is all for today.
Madam, small request, madam.
Yes, please.
In next class, if possible, can you add a little bit topic on back pressure?
Okay, I will do
And
that.
also, if possible, any small numerical related with back pressure.
Yes, yes, I will.
Thank you, madam.
Okay. Thank you very much, everyone.